Hey everyone, and welcome to This Explainer. Today, I'm putting on my elite ICPC coach hat, and we are going straight to the big leagues. Our mission in this masterclass is simple, but honestly, it's pretty profound. We are not here to teach you basic stack syntax. I mean, anyone can type push and pop in their sleep, right? We are here to train your brain. The ultimate goal is to hardwire your mind for instant pattern recognition. That way, you can walk into literally any top-tier FANG interview, look at a massive, intimidating wall of text, and just see the optimal solution hiding in plain sight.
Okay, let's dive right into this. The quote you're looking at really defines the fundamental paradigm shift we're making today. You know, when you first learn data structures, you're taught to process things linearly. You look at an element, you do something with it, and you move on. But a stack? A stack demands a totally different mindset. It forces you to think about deferred resolution. It's basically a mechanism to remember history that is actively waiting to be resolved. It asks you to perform a really simple thought experiment. What happens when I just don't have enough information right now, but I absolutely know I will get it later?
Here's our game plan for today. We're going to cover the deferred decision mindset, LIFO intuition, the 3 core stack patterns, monotonic stack mastery, a dry run of the largest rectangle problem, and finally, how to avoid those deadly interview traps.
All right, let's kick things off with Section 1, the deferred decision mindset, and how we move beyond immediate processing.
Think about the difference here. With immediate processing, kind of like using a sliding window, the decision about each element on the conveyor belt is made the exact second you see it. Zap, it's done. You process it and you forget it. But with stacks, it's a whole different story. Sometimes when we hit an element, we simply do not have enough information to act on it yet. We have to wait. We need to see what comes later in the array or the string before we can figure out what to do with the thing we're looking at right now. So the stack becomes your hourglass. It's a holding area that buys you time. It totally offloads your cognitive burden by holding on to a state, just waiting, because something in the future will eventually arrive to change its meaning.
Moving right along to Section 2, LIFO, Intuition, and Analogies. This is basically the call stack in real life.
To really get this, think about how a stack operates in the real world. Imagine you're making parathas. You cook the first one, put it on a plate. As you cook more, you just keep stacking them up. Now, when someone comes into the kitchen to eat, which one do they take? The top one, obviously. The hottest, most recently cooked paratha. That right there is LIFO in action. Last in, first out. And why does this matter for your interview? Because this exact logic governs the undo button in your text editor, the back button in your web browser, and crucially, the call stack and recursion. The most recently opened function absolutely must close and resolve before the older ones underneath it can finish.
Okay, Section 3, 3 core stack patterns. This is all about mapping those interview triggers.
Listen, if there's one thing to physically screenshot from this entire explainer, it is absolutely this table. Treat this like an interviewer's mental cheat sheet. When you're reading a problem prompt, the clock is ticking, right? If the prompt mentions nested or matched structures, your brain should immediately snap to a matching stack, like validating parentheses. If it asks for O1 access to a minimum or maximum while you're doing a bunch of pushes and pops, you're not sorting, you are doing state tracking. And if you see phrases like next greater element, next smaller element, or even days until a warmer temperature, boom, that is your golden trigger for a monotonic stack. Memorize these triggers and you completely eliminate that initial panic of not knowing where to start. Let's get into the heavy hitter, Section 4, monotonic stack mastery, and what I call the golden rule of reversal. So, a monotonic stack is really just a normal stack, but it plays by one extremely strict rule. Its elements must stay in a strictly increasing or strictly decreasing order. But I want you to really think about this for a second. What happens if a new element tries to enter and it breaks that perfectly sorted order? Well, the stack ruthlessly pops elements off until the order is completely restored. Now, when you use this in an actual interview, please do not just silently code it out. State your invariant out loud to the interviewer. Tell them exactly what condition is going to trigger a pop. It shows them you are in complete, absolute control of the algorithm's boundaries.
Now, knowing exactly which variant to use, increasing or decreasing, is where like 90% of candidates totally fail. So I'm going to give you a golden rule to forcefully anchor in your memory right now. Ready? The stack order is always the opposite of what you are looking for. Seriously, write that down. If you need the next greater element, you use a strictly decreasing stack. Why? Because it holds on to a line of smaller items until a big element finally arrives to resolve all of them at once. And flip it. If you need the next smaller element, you use an increasing stack. If you just remember this one opposite rule, I promise you will never panic and pick the wrong variant under pressure again.
All right, let's put this into practice. Section 5, the largest rectangle problem. We're going to simulate a dry run.
Let's apply everything we've talked about to LeetCode 84, the largest rectangle in a histogram. Imagine a bar chart. We're processing the histogram from left to right, and we are pushing the indices of the bars onto our stack as long as they keep getting taller. So this is an increasing stack. Because they're getting taller, their potential rectangle can stretch infinitely to the right, right? So they just sit there on the stack, deferred. Kind of like sand in an hourglass, just waiting. But waiting for what exactly? They are waiting for a smaller boundary to finally arrive and cut them off.
So what actually happens when that sequence finally breaks? A shorter bar arrives. And this shorter bar is our next smaller boundary. It triggers an immediate pop. The taller bars get popped right off the stack because their rectangle cannot possibly expand any further to the right. And guys, here is the absolute magic of this algorithm. The second you pop a bar, whatever is left sitting underneath it on the stack is its previous smaller boundary to the left. Just like that, you now have the exact left and right boundaries instantly. You calculate the width, multiply it by the popped bar's height, and boom, you found your maximum area for that specific bar.
Now I'm going to give you an absolute expert trick to guarantee your code is perfectly clean and absolutely wows your interviewer. It's called the Sentinel trick. Think about it. What happens if you reach the very end of the histogram and a bunch of bars are just still sitting there unresolved on your stack? Simple. You just append a dummy bar of height 0 to the very end of your array. Because 0 is mathematically smaller than absolutely everything else in there, it acts like a giant bulldozer. It forces every single remaining unresolved element to pop and calculate its area at the very end. No messy cleanup loops required. It's beautiful.
Let's wrap up with Section 6, Avoiding Deadly Interview Traps. Consider this your XFANG checklist.
What's really interesting here is the classic Socratic trap. Picture this. Your interviewer asks you to build a min stack. Now, tracking the minimum going in? That's easy enough. But if you just keep a single minimum variable, what on earth happens when that specific minimum element gets popped off the stack? Your variable is totally stale now. It's useless. How do you find the new minimum without scanning the entire remaining stack in an agonizing O(n) time? Really think about it. Answering this correctly is exactly what separates a junior developer from a total master.
The elegant fix here? Redundancy. You just store a tuple. As you can see, instead of pushing just the raw value onto the stack, you push a pair, the value itself, and the current absolute minimum at that exact moment in time. By doing this, every single level of the stack becomes completely self-contained. If you pop the top element off, you don't need to recalculate a single thing. The correct previous minimum is already sitting right there inside the new top element's tuple. You maintain perfectly optimal O(n) time. Finally, before you step into your next interview, I want you to run through this mental checklist like a pre-flight routine. Number 1, never ever access the top of the stack without checking if it's empty first. That is an instant runtime error and a terrible look. Number 2, in monotonic stack problems, store the indices, not the actual values, so you can actually calculate widths and distances later. Number 3, lock in your monotonic direction early. Remember the golden rule. The stack order is the opposite of what you're searching for. And number 4, if you aren't using our Sentinel bulldozer trick, for the love of coding, do not forget to manually handle the elements stranded on your stack at the end of the loop.
So I'll leave you with this final thought. Mastering DSA, it is not about rote memorization. It's about looking at a paragraph of text and seeing the invisible structures running beneath it. When you truly understand that a stack is simply a holding area for deferred decisions, an entire world of optimal solutions just unlocks for you. You don't have to fear the next greater element or the largest rectangle ever again. So ask yourself, are you still trying to just memorize code, or are you finally ready to conquer LeetCode by seeing the patterns hiding in plain sight? Take this framework, apply it, and go crush that interview. See you in the next explainer.